Okay, look at number 3. So here's something really interesting. I want you guys to realize that. All right, first off, I want to blow your mind a little bit. Did you guys know that the idea of 0 had to be invented?
Yeah.
Because it's an idea. They all had to be freaking invented. There were civilizations, for example, the Babylonians, for most of their existence, they didn't have a symbol for 0. So if they wanted 407 chairs, they wouldn't write this. They would actually write, these were the symbols for ones, and this was their symbol for 10. So this would be like 22. Bam. Isn't that neat? Okay. They also had a base 60 system instead of a base 10 system. We're not going to go into that, all right? All I want to know is, if they wanted 407 chairs, they'd leave space here and hope to God the other person understood they meant 407, not 47. All right, so what's this got to do with what we're doing? All right, I don't, oh yeah. Look at number 3. I got 2x cubed minus x plus 3 over x plus 1. If I go to set this up to long divide, this is like 47 when it's supposed to be 407. What is, in our system, what does that mean? Very specifically, what does that 4 mean exactly? You got 4 hundredths. What does this mean?
0, 10.
No 10s. So we have a placeholder because we don't have any of that shit. So what am I missing on the top?
Squared.
X squares. So I better put a 0 placeholder there, or else things are going to get a little bit freaky and I'm going to mess up. So what I mean is this. When I go to write this as long division, put 2x cubed plus no x squares minus x plus 3. Become a 3. All right, let me stop for a second. We're going to see very quickly why that placeholder is useful. Is it absolutely necessary? To be honest, no. But my God, if you didn't put it there, you'd have to really be on top of it, like, oh, put it in the right place. Yeah.
Oh, I was going to request if you could use a black marker.
Sure. Maybe. All right, let's see what I've got. This one I have a feeling it's not going to work. Yeah, sort of does.
Thank you.
Maybe. Hold on. Let's see, I think you might be working. Ooh. All right.
There's just lots of glare on the board.
I'm with you. I understand.
Thank you.
Sure. All right, so somebody help me out. How do I determine what to put here? Yeah, x times what is 2x cubed, 2x squared.
Oh, so it's squared.
2x squared times x is 2x cubed, which is kind of a check to make sure you did the first step right. It's supposed to be. That's why it's there. 2x squared times 1.
2x squared.
See, if I didn't put that there, there sort of wouldn't be anywhere to put it. Okay. And then I change the signs. Which is the same step we always do. We would subtract, which is another way of saying change the signs. Like it. If you weren't here yesterday, I'm sorry. You gotta want to go take a look at that video. So then what happens?
Cancels,
You have negative 2x squared, and then I
See how many times I'll bring down.
Bring down negative x.
So what am I going to put here? X times what is negative 2x squared?
Negative
Negative
2x.
Let me stop for a second, everybody. Every time you're about to put something here, that's what you're thinking. X, this thing times what is this thing? And then negative 2x times x is of course this, because that's why you put that there. Negative 2x times 1. And then I change the signs. I really want you, if you think that I'm doing different steps than if they were numbers, you're wrong. You need to come see me or ask a question now. We're doing every step exactly the same. Why? I have to. X's are numbers. They have to work the same way. Yes?
Could you explain the beginning of the problem again?
Okay. So, in the beginning, there was this. Which, are you cool with putting the 0x squared? Placeholder.
Yeah.
Right? And then you do basically the same thing we just did. X times what is 2x cubed?
2x squared.
2x squared. So now you're caught up. Then that times this is here, that times this is here. Subtract, so I change the signs.
Okay.
Combine, bring down. That times this is this. Negative 2x times 1 is negative 2x. Change the signs. This is called an iterative process. The thing you're using at the moment changes, but the actual thing you do with it doesn't. Right? Multiply, multiply, change the signs, add. Bring down, multiply, multiply, change the signs, add. Right? So what do you get here? Those go away? X plus 3. X times what is X?
1.
That's crazy. And so 1 times X is X. 1 times 1 is 1. Change the signs.
T.
T.
Plus 2 over x plus 1.
Yeah.
How'd you get negative 1?
Are you cool with where I got 1 from? 1 times X is X.
Okay.
1 times 1 is 1. Subtract, just like normal long division. And I kind of don't like using the word normal because this is the same long division. Why is it a little worse to keep track of? Because there are numbers I don't know. So of course it's going to be a little worse, but the process fundamentally can't change. They're still numbers. I just don't know them. So of course it's going to be a little bit freakier. Right? All right. Do you guys wish there was a shortcut to this? All right, we're about there, almost. Make you suffer through one more. Try to do number 4. You guys got this sheet, right? Anybody need this sheet? Yes, on the other side. So try out number 4, guys. Yes.
An example for like this one, can I open it like like this one? X minus 16, then x squared.
We don't know that yet. No.
Yeah, but can I use it?
No, we don't know it yet. You can't use something we don't know yet.
No,
Even if you know it. I don't care. You got to use it in a long division.
I know.
Okay.
But can I use this like to check or something like this?
Do I know? Sorry.
To check if it's the same.
So you're factoring this, right? Or you're sort of. Or yeah, you wouldn't be done. So you could check it sort of, but not necessarily because it might not go in evenly. So
Just when we have like we have 2 or 3, but just we can use this. Do not use this. We have remaining.
so officially you can't use that at all yet. At all.
Yeah.
If you want to try to use it on your own to check some things, and you got to be careful because it's not always going to be perfect, then sure. Yeah.
Yeah.
Yeah, okay. Keep going. I mean, that's right so far. But now, so now what x squared times what is 2x cubed? That's what goes here. Yeah? Oh. So the thing is, if you're missing something out here, I want you to realize why it doesn't matter. You don't have to put a placeholder in
Over
it.
here, write it over here.
You guys doing all right? Okay.
Because you can't subtract 4x from 4x from x squared.
Yeah.
So like keep like terms.
That's right, do I do it now? Well, like, why?
So
All right.
So only work on these two then.
so like
So just work on this, and then bring this down, and then I'll work on this in the next step, is what you're saying.
because they have to stay in the same step.
So guys, you could put 0x here, and I think the book might even say so, but screw that, I don't need that shit here. Why do I need it inside so that I have a place to line up like terms? Out here, it doesn't really matter. I don't put anything out here, so it doesn't really matter. Let's see why that's not true. Let's see what happens. X squared times what is 2x cubed?
2x.
2x. 2x times x squared is 2x cubed, just like we just said, Jeff. All right. 2x times negative 2?
Negative 4x.
Negative 4x. Bang. So you don't need a 0, you just make sure you put it with the like terms. Don't put it here and suddenly make it come out to be 0 or 8 or whatever. No, they're not like terms. That's x. Can't go with x squared. And then I change the signs. Those cancel like they always have to. You guys see that? And then this is so x squared times what is negative 4x squared? Negative 4, it's craziness. So negative 4 times x squared is negative 4x squared. Negative 4 times negative 2 is 8. And then change the signs.
X minus 5 over x squared minus 2.
By the way, how did I know to stop here?
Because x, or
X,
x squared can't go into x.
The degree of this is smaller than the degree. There's no way I can multiply this by something and make it the same as that because that's missing x's that guys has. So it's if the degree of this is less than what you're dividing by, you stop. That's your remainder term. I wish I knew. Oh yeah, right here, right here. X squared times what is negative 4x squared? Negative 4.
Excuse me. Can you put hold on this one and do it again?
You could totally, I'm not going to. I won't. You can. The book says to do it. I want you to see why it's not necessary. I don't need a placeholder out here because I don't line anything up out here. I just have to be sure to put my stuff in the like terms, that's all. So if I had a 0x here, all that would do is 2x times 0x is 0. There would have been a 0x squared here. Ooh, right? Now if you like that better, you can do it that way. I'm just telling you, you don't have to. Okay. All right, so let's talk about, what time is it? All right. I gotta leave a little bit early today because, well, we won't get into the whys. All right, well, that's enticing, John. So let's talk about a possible shortcut for this process.
Pleasure.
Now the thing about this shortcut is it only works, it would not work on the last one we did. Because what's the degree of the bottom there? On the last one we did, what's the degree of the bottom?
Oh,
2. So it only works if the bottom is degree 1. And it only really works directly if the bottom has just 1x plus or minus something, right? So like it would work on the first one. Let's look back at the first one here. Now we did this together already. I'm going to do it again real quick and then I'll show you the shortcut. But I just wanted you guys to remember how this thing worked before. Quick doesn't mean different language. there's that thing. All right. So, do you see how this step here is completely unnecessary? Isn't that always going to like cancel? All right, so I want to make a process where this doesn't even show up. And what am I thinking about when I'm saying x times what is negative 4x, for example? I'm looking at the numbers. 1 times negative 4 is negative 4, right? I shouldn't have to rewrite the variables all the damn time. So, this is kind of cool. This is the thing I called, it's just called this. I told you it was called synthetic division. So it's going to look like this. So I don't watch hockey, but I borrow a little something from it. I call it the penalty box. So let's see what the shit I'm talking about. Little camera, you can do it. I can't. Yes, you can. All right. So, a couple of things. You guys agree with me that some of this stuff is really, really unnecessary. There's a lot of freaking writing. If I had a few more terms here, good God, I got to turn the paper this way or something, right? Okay. So, the most important things then really are the coefficients. So here I'm going to put 1, 2, 20. Because they're in descending order there, right? And I'm not missing anybody, so I don't have to put a 0 over here anywhere. Another thing is I have to keep remembering to change the sign. So for example, 1 times 6 was 6, but then it became negative 6. Negative 4 times 6 was negative 24, and then it became positive 24, right? So the process says, all right, so why not just change the sign once in the first place? So this doesn't really matter, believe it or not. So I'm going to just put the 6 in the little penalty box, but I'm going to change it to be negative 6. So I'm changing the sign in the first place. Okay. And it doesn't make any sense yet, so I'm going to keep going. Just, you're all like, you wrote numbers and put a little freaky thing there. So here's the idea. Whatever, if this would have been a 2 here, if there would have been a 2 right there, what would have been different? That would have been a 2, right?
Yes.
So whatever number this is going to be part of the answer. So you just bring this number down. Bring it down. Bam. Now, negative 6 times 1 is negative 6. 2 minus 6. 2 minus 6 is negative 4. Negative 6 times negative 4 is 24. 20 plus 24 is 44. Black magic. No.
Witchcraft.
I was going to say fuckery, but I decided not to.
What did he say?
Fuckery. Black magic. The way you have to interpret this, because it's a shortcut, number one, it can only handle very specific situations on the bottom. The minute I put a square there, the whole thing goes to shit. If I put a 4 there, it semi goes to shit. If it's x plus or minus something, it works beautifully. Right? So one reason why it works so well is because we really restrained what it works for. So I don't have to take care of all these different situations. Secondly, how the hell do you interpret the answer? So what did this mean again? What's this 1 mean here?
X
No.
squared.
X squared. And this meant x, and this meant number 20. And I'm dividing by x stuff. So I'm going to lose an x. So the way you interpret the answer is 1 degree less. So this is 1x, a degree less than what it started off as. Minus 4 is a number. And then this is going to be the remainder term.
Is that always the case?
Yes.
So like if there was no remainder, that would have ended with 0?
Exactly.
Okay.
So having a 0 there means it's actually perfectly factorable. Yes.
Good.
Let's do another one.
Yeah.
I think that's probably a good idea. All right, I want to do it the same way. So So what if I had, let's say x cubed, let's do 5x cubed, oh, that could be, well, screw it, Jeff, it's fine. 5x cubed minus 4x squared minus 3x, so it's my fault if this thing goes really to shit, but oh, divided by x minus 2. Oh, this could be exciting. All right, so how do I set this up?
You put your little plus box,
What am I going to put in my little box?
+2.
Yes. So really the shortcut is whatever makes this 0. Do you see that? Whatever makes this 0 goes there. But remember, why does it make sense? Because I have to change the damn sign in long division every time. Why don't I change it right at the beginning and forget about it? Yes? Are you stretching? Okay. It's a very weak stretch. That's what I thought. So what goes here?
5,
5,
-4,
-4,
-3,
-3,
6.
6. So there's going to be a bunch of multiplications and additions, which is really what is involved in long division. When you look at it, you put a number, you multiply, and then you add after changing the sign. So bring the 5 down. 2 times 5 is 10. Add.
6,
2 times 6 is
12,
12. Add.
9,
9. 2 times 9 is
18,
18. Add. Gave up on it.
Oh, so you multiply, then you add.
Yeah, and the reason I bring that first number down is if I was going to pass out, if I was going to do this long division, which I don't feel like it, what would I put here? 5 almost doesn't matter. So that number is going to be part of the answer. That's why it just comes right down. And let's see, a couple more steps here. 5x squared times x is that. That's why we put it there. 5x squared times that is that. Change the sign. -4 plus 10. -4 plus 10. See, that method captures the most important parts of all this shit. And this is exactly what math people love. We're like, I don't like to write a lot because I can't do it well. And I'm impatient. So let's make a method where bam, 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 bam. We love that shit. How do I write the answer now?
5x squared
Good, because it was cubed, lost an x. So now it's x squared.
plus 6x plus 9 plus 24 over x.
Yeah, that's going to be my remainder term over the thing I divided by. Crazy sauce. So let me give you this. This is, oh, I don't know. This could have been colorful, but it isn't. It's too bad. It's too bad.
I mean, I get it.
Way
I'm sorry, buddy. I'll walk right past you.
Yeah, I get it now. That's pretty easy. See, I like it a lot.
Can you repeat like this? 5x squared and just this one.
So it was x cubed, right? I divided by x stuff, so I should lose an x in my answer. Right? In fact, every time we do this, x goes into this 1 less x times. Of course it does. Because there's an x, I need 1 less x here, so together they make all these x's. It's always going to go down by 1 degree. So that shortcut just captures everything that would happen. And just gets right to the point.
So the, oh, sorry.
What? What's up?
That's you.
Oh.
What about 6?
What about 6?
6x.
Yeah. Why? I don't understand.
Because for
Every term is a degree down. Right?
Yeah.
So that's going to be a degree down. That's going to be a degree down.
for x. The
Yes.
number is the same, we use the same, these numbers.
Yes, because the answers, what's this? This is the coefficients of the question, right? This will be the coefficients of the answer at the end. So that's why you can just put them right as coefficients. And what coefficients of what? Terms that are a degree less than what they were
So
at the
you said
beginning.
We're gonna change the sign, which,
I did, right there.
just this one.
I only had to change it once. Again, why? Because right here, there's a way we could sort of, I'm trying to play around with a different way to teach this, but I don't want to, if I play around with this shit too much, people get confused, but I could have changed the sign to begin with already, but I would have to change both signs. It gets really weird. If I would have changed the signs at the beginning, then this would have been easier, but then it does make it harder to keep track of what should go up there anyway. So I have to change the sign each step, right? And this process sort of says, I don't really need to keep track of the letters. So I could have put a -2 here, but then we thought, holy shit, I could just change the sign once here, and I never have to change it again. Instead of changing it every time. That's beautiful. I know I'm a little biased. But I'm also right, so hey. All right, so I gave you, on the handout is a worked out example here in the middle with little explanatory notes. There's a worked out long division problem, and then I redid it at the bottom, synthetic division. I purposefully gave us a remarkably long, disgusting one, right? Because this process scales quick. This process, if I had more shit, it would just be the same thing, a little longer. Whereas this, I put more shit and I do a long division. Oh my God, right? As you can see on this, maybe. Okay, I like it. I'm trying to get you to realize that this isn't just another thing to know. It's a better method built on. Now again, why do I still need you guys to know how to do long division? Because this doesn't always work. So we still have to know how to do this. It's just if I have 1x plus or minus anything, I can do this, kick ass. Okay, remember. All right, I think that's it. That's enough for today. I want to get over there before it's all over. All right.
Excuse me. So in the test, there is no other any way we use it, like this one or this one.
I'm going to ask you to do both ways. Because both ways are a part of what we learn. Yeah.